guys, this is the third video in my sort of review refresh series of videos. Going into AP Physics 2, I would say energy and work is the idea that's going to come up the most. It's the AP Physics 1 topic that we're going to use all throughout the entire year. So it really is important that you have a solid foundation in this. If you took freshman physics, we talked about conservation of energy and the energy types, so you have kind of conceptual understanding of it. If you took AP Physics 1, you handled it a little bit more mathematically. So I want to make sure everybody has the same equations. And I also want to make sure that everybody has the same perspective on this, which is that energy and work is really the most powerful way to solve almost every physics problem. Despite the fact you learn about kinematics and forces first, they're really limited and sort of clumsy when it comes to solving problems. Energy and work is much more elegant, much more advanced typically. So this is a really good unit for you to review and try to get as comfortable with as you possibly can. The essential questions for this unit are, first, what is energy and what is work? Second, what kinds of objects have kinetic motion energy and what are the relationships that make up the equation for K, which is the symbol for kinetic motion energy? 3, what kinds of objects have potential gravitational energy and what are the relationships that make up the equation for UG, which is gravitational potential energy? 4, how do you calculate work and why does it matter that force and distance are both vectors in that equation? And 5, how can you use work to figure out the amount of energy an object has at any point in time? So let's start off by talking about energy. There are 3 symbols that you will see on the equation sheet for energy. I wish that E was more commonly used with subscripts because that would make everything very clear. But you will also see K, which stands for kinetic energy. So E is sort of more generic energy. K is often used for kinetic motion energy, and U is for any kind of potential energy, of which there are several types represented on the equation sheet. The risk here is that you will not realize that E, K, and U are all the same thing. They can be added, subtracted from each other, transformed into each other, and they're all the same fundamental property, which is energy. And when you see any of those variables, make sure you take a close look at the operators and subscripts to go along with them to help you figure out more specifics. Energy is a really tricky thing to define for scientists. I'm going to stick with a short and sweet. It's the ability to do work. And you should also know that there are 2 big categories of energy. I think when you first learned about energy in middle school, you learned that there are 2 energies, which are kinetic and potential. But it turns out there's tons of different kinds of energy. But we are able to categorize them into those 2 categories. So our kinetic energies are any energies that involve moving objects or parts of moving objects. So obviously the standard one is motion kinetic energy, which is just the whole object is moving. In thermal energy, which we'll cover a lot in this class, you have moving particles within the object. Rotation kinetic energy involves spinning objects, waves are oscillating objects, etc. Potential energies, on the other hand, are energies that store up that ability to do work. Gravitational is one type of potential energy, but there's lots of other types, including chemical energy, nuclear energy, electrical energy, and others. Energy is a scalar variable, which actually makes it way easier to solve problems with because you don't have to keep track of what direction things are moving. And it's always going to be either 0, so you can have no energy or no energy of a specific type, or it's going to be a positive value. You can't have negative amounts of any kind of energy. The SI unit for energy is the joule, which is a capital J. In chemistry, you used a different unit, which was a calorie, but we're going to be using joules. You can convert directly from joules to calories and vice versa. And a joule is equivalent to a Newton meter or kilogram meter squared per second squared. Incidentally, energy is not possible to measure directly, which is one of the challenges of it. So you have to sort of calculate energy from other variables that can be measured. In AP Physics 1, you focused on 2 specific energies, which were the kinetic motion energy and the gravitational potential energy. And so I want to review those two here. But I do want to point out that they're not the only energies, they're not the only important energies, they just happen to be the first two that you learned. We're reviewing them now because the equations for those two energies are very straightforward and easy to use, and they will come up in this class. In fact, the equation for kinetic motion energy gets used many, many units in this class. So if you did not take AP Physics 1, and this is a new equation for you, you definitely want to take note of it, and the variables and relationships that go into it. So kinetic motion energy, K, is the energy of any object that is moving relative to any kind of reference point. And that can be a tiny, tiny object like an atom. Atoms themselves have kinetic motion energy, and so do electrons, all the way up to like a massive galaxy that's moving, relative to another galaxy in space. K has a linear relationship with the object's mass, so the bigger the mass of an object, the more kinetic motion energy you would expect it to have. And it has a quadratic relationship with the object's velocity. We didn't talk much about quadratic relationships freshman year. Hopefully you've seen it in math class. But in any case, it just means that the v is squared in that equation. So velocity is more important than the mass when it comes to calculating K. This is the equation for K given on the equation sheet. You'll definitely want to put a nice big box around that one and star it because we'll be using it lots this year. That 1/2, it's easy to figure out that derivation if you're kind of curious where that 1/2 came from, but in general, kinetic energy is equal to 1/2 times the object's mass times its velocity squared. If you run through the units for these variables, mass is kilograms, velocity is meters every second, so you end up with the unit of kilogram meters squared per second squared, which is consistent with all the other kinds of energy, which is a good thing because energy, as I said before, no matter what variable we're using, in this case K, but it's all energy. The second kind of energy that has an equation that is a good idea to understand before you head into this class is gravitational potential energy. All kinds of potential energy are represented by a capital U in the equations, and they get subscripts to indicate the type of potential energy. So in this case, we're talking about UG, which is gravitational potential energy. Gravitational potential energy is the energy stored up in the gravitational force field of between two objects that are pulled apart, or I guess brought closer to each other. Because two objects with mass are attracted, by forcefully separating them, you are storing energy in that force field, kind of like pulling a spring apart would store up energy in the spring. You can have a little tiny amount of gravitational potential energy, for example, a book that you're lifting above the Earth's surface, or you could have a lot if you had two huge objects separated by a big distance, like a system of binary stars. There actually is an equation to calculate gravitational potential energy generically of any object in the solar system. However, I'm not going to get into that equation yet. We'll talk about that later on in the year. The equation that you used in AP Physics 1 and the one that I'd kind of like you to understand starting off the year has to do with changing the gravitational potential energy of an object near the Earth's surface. So specifically, we're talking about lifting things up or dropping things near the surface of the Earth. So the equation that's on your equation sheet is for delta UG, because it's only telling me how much the gravitational energy is changing. It's not calculating the absolute amount of it, just how much it's changing. And there's a linear relationship with the size of the object that you're moving around. So if we're talking about the book, that would be the mass of the book. Obviously, the bigger the book, the more gravitational energy you're expecting it to change as you move it around. That object is often called the test object because it's the thing that you are physically moving. Of course, all motion is relative, but in any case, usually you think of the book as doing the moving and not the Earth itself. The second relationship is another linear relationship with the gravitational field of the other object. So the other relevant object in our example is the Earth, and Earth's gravitational field depends on the mass of Earth and the size of Earth, etc. And we've already learned about that value. It's a constant. It's the same as the acceleration of objects near Earth. So that's that little g that we learned about in the previous slideshow. And then the third variable that also has a linear relationship is how much you change the distance between them. So we're talking about just how far apart their centers are. And if you look at the equation, you'll see those three linear relationships. We've got delta U linear with mass, linear with G, which is always going to be 10 when you're talking about Earth. And then the last one is a delta Y. They put a Y on there because they want you to understand that this object has to be sort of moving in the Y direction. It has to be moving up and down. If I hold that book and just walk along the Earth, I'm not giving it any more or less gravitational potential energy because I'm not changing how far apart those objects are from each other. So specifically, the distance is represented by a Y in this equation because you're moving it vertically. If you go through and do the math with the units of the variables in this equation, you'll find it all works out again. We've got a kilogram times a meter per second squared times another meter. So we have kilogram meter squared per second squared, which is the same as a joule. The other variable that you need to understand thoroughly is work. The symbol for work is typically a W, although, as you'll see in a second based on the definition, if you ever see a delta E or a delta U or calculate a delta E or a delta U, that's the same as finding work as well. So you should know that those are all synonyms for each other as well. Definition of work is the change in energy. It's kind of circular. So if an object's energy is changing, work is either being done on the object or by the object. No matter whether that change is like internal, so I'm turning my own chemical energy into kinetic motion energy, or if it's external, somebody else is pushing me and giving me that kinetic motion energy. Either way, we would define that change in energy as work. Work is a scalar variable. It's exactly the same as energy, so it has no direction as far as up, down, left, right, etc. However, it can be positive or negative, and the sign on the work tells me whether the object's energy is increasing for a positive work or decreasing for a negative work. So if, for example, you give me a push on the swing, then it would be positive work on me because I'm gaining energy from your push. If I then sit there for a long time and the swing eventually slows down from friction, that's going to be negative work because the friction is reducing the amount of energy in my system. SI unit for work are going to be exactly the same as they are for energy because work is a change in energy, so all the same things we've been seeing on the other variables. So there's two equally valid and important ways to find work, and you really need to be versatile and flexible about these things, be able to use both of them and use them together. One of them is a very conceptual understanding of work, and the other is the mathematical equation for work. So the first, as I mentioned before, is that work is a change in energy. So if you know how much energy an object has at 2 moments in time, you can find the work just by subtracting the initial energy from the final energy. And so that's kind of like really understanding the heart and soul of what work is when you calculate work that way. The second way is that whenever an object is moving, all the forces acting on that object that have parallel vector components do work. I know that's kind of a mouthful, and I'll explain more what that means in a minute. But mathematically, work has a linear relationship with forces on objects, and it has a second linear relationship with the distance the object is moved. The equation on your equation sheet is an incredibly important one. So it has both of these sort of ways of calculating work in it. First, it says delta E equals W, so that's a reminder that work is defined as a change in energy. And then there's two equations that go along with that. Force times distance, and those little parallel lines in between the force and the distance are telling you that we are only allowed to use the parallel parts of those, which we kind of mentioned that in that last slide where we talked about how if you carry a book horizontally around the surface of the Earth, you're not changing its energy, right? In that case, the distance is kind of in the x-axis, but the force that you're exerting on it is up and down. So there actually would be zero work done because there is no parallel force to the distance that it's moved. Mathematically, it's also sometimes convenient to calculate this using the angle between the force and the distance. And so that equation FD cosine theta kind of does that automatically for you. It calculates what is the parallel portion of the two vectors, the force and the distance, and those are the only things that would be used in calculating the work. So we'll do an example in a second. Okay, so here's an example of calculating work and seeing how that parallel vector part works. We've got a box that's being dragged along some sort of rough ground by a rope at an angle. So we're going to start by drawing a free body diagram of the box. We've got four forces acting on the box. We've got gravity pulling down because it's on Earth. We've got the normal force from the ground holding it up. We have some friction from the ground because it's rough backwards. And we have a tension force along an angle from the rope that the person is pulling. We also have to have that object moving a distance because by definition, no work is done if the object is not moving. Its energy is not going to be changing if it's just sitting there still on the ground. So in this case, we'll have it move a distance d horizontally along the ground in the same direction that the person is pulling. So the first thing I would do is consider the amount of work done by the normal force and the gravitational force. Even though those are big forces on that box, they don't do any work on the box because they are perpendicular to the distance that it's moved. Right? Those forces are acting up and down and it's moving sideways. So those two forces are not actually changing the energy of the box. Gravity, it's just hanging out, pulling down, but it's not giving the box any more energy, and neither is the normal force, which is pushing up on it. So those are easy to handle. They have no work. Next, I would look at the work done by the friction force. So the work done is equal to force times distance, making sure they're both parallel. Now, because the distance is horizontal, fully in the x-axis, and that force is also an x-axis force, you can just find the product of those two forces, or sorry, those two vectors, and that would be the work. You'll notice I put a negative sign there, and that's because the force and the distance are in opposite directions. We're moving to the right and the force is to the left. So one of them has to be negative regardless of which one you want it to be. It's also useful conceptually to think about how friction's function in this case is to slow down the box, take its energy away. If this box is moving, it's got some kinetic motion energy and friction acts on it, it's going to be moving slower and slower and slower until it's lost energy. So it makes sense that that work is going to end up being a negative value when we've done the calculations. The tension force from the person is going to be providing positive work, but we can't use the entire amount of force because it's not all parallel to the distance that we're moving. In fact, we're only going to be using the component of that force that is in the x-axis, which is parallel to the distance that it's moved. If you need a refresher on resolving vectors into components, you should check out the math video that I'm going to be posting a little bit later on. But in any case, if we want just the chunk of that force that's in the x-axis, we could find that using trig if we knew that angle to horizontal. So the x component of that force is equal to Ft times the cosine of theta, which means when we calculate the work, it's going to be Ft cosine theta, that's the horizontal part of that force, times the same distance that the object was moving from before. You'll note that I put a positive sign in front of this because the person pulling the rope is adding energy to that system. It's working to give that box more kinetic energy or speed it up, and so it should be a positive work. You can also do a little overall analysis of this box. You could figure out how much kinetic energy the box is gaining if you have the values of all those forces. So the overall change in kinetic energy is going to be equal to the work done by friction and, well, I could say the work done on friction, the work that friction is taking out of the system, plus the work done by tension, which is going into the system. And if you had those values, you would then know how much the kinetic energy of this box is changing, which you could actually use to calculate the velocity of the object using our kinetic energy equation that we learned about earlier in this video. All right, so that was it. That was a lot. Take a few minutes and revisit the 5 essential questions from this video. And make sure that you've got a working understanding of energy and work and how to get back and forth between them. And if you are struggling with any of the content on the slides, especially that last bit about those things being parallel with each other, please come see me at a tutor time or any of the other times I'm available. I would be more than happy to go through those things again. Thank you.